Today, I will be explaining my medical electronics project. This is my circuit and it's supposed to obtain the sound output from a stethoscope which completes to be a biomedical processing system. For simplicity, the schematic diagram is split into 4 stages. Stage 1 consists of TP1 to TP2, Stage 2 consists of TP2 to TP3, Stage 3 consists of TP3 to TP4, while Stage 4 consists of TP4 to TP5. I will be explaining my circuit in stages. In stage 1, IC-A1 is a TL072 IC that is a dual low noise JFET input general purpose op-amp. The supplied voltage gain is between 10 mV to 1 volt and does not provide current. C1 is a 10 microfarad coupling capacitor that blocks out DC bias voltage and only allows AC bias voltage to pass through from the input. R5 and R6 is a voltage divider that acts as a level shifter which provides half the supply voltage of 4.5 volts for the op-amp to be working at a single supply mode. The level shifter takes input signals at one voltage level and transforms output voltage to a different voltage to prevent damage to the components and allow better compatibility. Before the level shifter, the single supply mode will cause the negative side of the sine wave to be cut. Since the circuit needs to bring the signal from an electro-microphone up to a level suitable for a line input, the level shifter shifts the sine wave so its line level becomes 4.5 volts, so the negative side of the sine wave would be visible. IC-A1 is a pre-amplifier which is a fixed-gain, closed-loop, non-inverting op-amp, and resistors R2, R3, and capacitors C2 and C3 form the passband filter. The passband gain is 23 using the formula of 1 plus R2 over R1. Based on my readings for the output of stage 1, when looking at the frequency, we can see that as the frequency increases, the gain would also increase until a maximum of 23 at 100 Hz, the same as I calculated before. Frequency higher than 100 Hz would cause the gain to decrease. Gain at 23 would be at 27.2 decibels. Based on the frequency response curve, the minus 3 decibel line would be at 24.2 decibels, so the low frequency would be at 20 Hz while the high frequency would be at 1.1 kHz. The bandwidth would be calculated to be at 1080 Hz. To set up stage 1, set power supply DC source to 9 volts and connect it to the circuit. Next, set the function generator frequency to sine wave of 1 kHz and 200 mV peak to peak. In this clip, we can see that I got an output voltage of 3.52 volts. Lastly, C4 is also a coupling capacitor which has a similar function to C1, which blocks out DC bias voltage and only allows AC bias voltage to pass through. Moving on to stage 2, IC1B shares the same IC TL072 as the first stage. It is a power amp that is a negative feedback loop amplifier, so a portion of the output voltage of the amplifier is returned to the input with a 180 degrees phase inversion. The trimmer controls the feedback signal that can reduce the overall gain of the amplifier, which can function as a linear amplifier and will not saturate the output voltage. In most audio systems, a power amp, as shown in stage 2, requires a preamp, as shown in stage 1, to function optimally. By dividing its amplification process, the preamp handles delicate signals, noise reduction, as well as volume and tone, while the preamp delivers high power and strengthens signal. Resistors 9 and 10 are voltage dividers that acts as a level shifter with functions as discussed before in stage 1. To set up stage 2, we will place oscilloscope probes in both TP2 and TP3 and leave the power supply and function generator untouched. There, we can get an output voltage of 6 volts. By turning the trimmer, we can see how the output waveform is affected. By adjusting the trimmer, the waveform output will be amplified, and at some point, the waveform will become saturated and be cut off. Moving on to stage 3, the IC2A uses a second IC TL072. Coupling capacitors C5 and C8 blocks out DC bias voltage and allows AC bias voltage to pass through. Resistors R11 and R12 are voltage dividers that act as level shifters with functions as discussed before in stage 1. IC2A forms a Sallen-Key second-order low-pass filter which is made out of two low-pass RC networks. A low-pass filter allows only low frequencies to pass through while rejecting all the high frequencies. As the lowest frequency can pass through a low-pass filter is 0 Hz, the bandwidth of a low-pass frequency coincides with its cutoff frequency given by this equation. Based on this table, we can conclude that when frequency is at 500 Hz, the filter is at about unity gain. But once the frequency is about 500 Hz, gain and the output will start to drop. So, based on the frequency response curve, the minus 3 decibel line would be at negative 3 decibel. The high frequency will be at 1.2 kHz, and therefore the bandwidth would equal to 1.2 kHz minus 0, which is 1.2 kHz, which is similar to the cutoff frequency calculated. To set up stage 3, we will place the oscilloscope probes in both TP3 and TP4 and leave the power supply and function generator untouched. There, we can get a filtered output voltage of 4.4 volts. The output waveform at TP4 will be determined by the output waveform at TP3. So, by turning the trimmer in stage 2, we can see how the output waveform is being affected. As mentioned earlier, when frequency is below 500 Hz, the amplifier will be at unity gain. However, in this case, unity gain is not applicable as frequency is set at 1000 Hz. Hence, there is an output voltage drop from TP3 to TP4. In the final stage, stage 4, IC3, ICLM386N-1 is being used. It is an audio amplifier that drives a speaker, and it is supposed to be working as a single supply mode internally, so no additional voltage is required. Capacitor C15 filters out high frequency that is above 40 kHz. Without it, the waveform output would be slightly unstable. Capacitor C13 is a coupling capacitor which filters out DC bias voltage and allows AC bias voltage to flow through. The input will first go through the trimmer P2 where pin E has full amplitude while pin A and S has zero amplitude of the input waveform. To set up stage 4, we will place oscilloscope probes in both TP4 and TP5 and leave the power supply and function generator untouched. There, we can get a voltage output of 7.04 volts. By adjusting trimmer 2, we can control the output at TP5. The final output would then be the maximum sine wave without being saturated.